Hello world, welcome back to this tutorial on writing a programming language compiler. Now in the last video we've talked about the LL method of creating a computer program from a context-free grammar. And the LL method is relatively simple and it works okay, but in my opinion the LR method is really much better, and that's what we are talking about today. If you want some image about how to think of this, if you have your start symbol up here, S, and the program code that you're reading down here, then the LL method worked like this. You called a function for S, and then depending on the look ahead, it would choose one of the productions and use that to select things like, okay, this terminal might be something from down here, and then it might need to recursively call another non-terminal function. Like this could be an if, and then here we have a Boolean condition, and then maybe, I don't know, a while. And that's the Boolean condition would then do something down here. And that's how LL works. It works top down by starting at the start symbol and then always selecting the next level that it's going into. The LR method is I would say it's a bottom-up parsing, because what it does is it looks at the stuff down here, and every time it finds something that matches one of the production rules, it then generates a node for the predecessor and then builds the tree bottom up from that. Okay, and how does it do that? The process of building this tree like that. I mean, Bison doesn't actually build a tree on the heap. It just executes functions in an order that would correspond to that tree. And if we want to have that tree on the heap, then we need to build that ourselves, and we will talk about that in the future. So as I said before, context-free grammars are equivalent to so-called push-down automata. And push-down automata are like automata. So you have states and transitions, a start state and final states. And unlike a normal automaton, a push-down automaton also has a stack that it can use. Okay, and this is the stack, and this is our token stream. Okay, so this is the data that we get from the lexer, and this is our stack. Let's say if open parenthesis a greater b close parenthesis, and so on. Okay, so this is a token stream that we get, and here we have the stack. And an LR parser now always does one of two things. It either takes something off the token stream and pushes it onto the stack. That would be called a shift operation. And let's say that we have shifted a few things. So we've shifted an if, open parenthesis. Let's say instead of the a and the b, we have our non-terminals for arithmetic expressions. Okay, a greater, so one arithmetic expression greater than another arithmetic expression. Then the other thing that an LR parser can do is it can say, hey, this here is the right-hand side of one of these operators, relational expression, arithmetic expression greater arithmetic expression. And then the LR parser can decide, okay, I take this stuff off the stack and replace it with an R. Okay, so if the right-hand side of a production is the right-hand side of the stack, then it can decide to take that stuff off the stack and replace it with the left-hand side of the production. Okay. And then we had this rule for a Boolean, which said relational expression is a Boolean expression. So the next thing we could do is we could take this R off the stack, make it a B, then shift the close parenthesis and keep on. And then occasionally if open Boolean close statement will be one of the production rules for a statement, and then that will be reduced to a statement. And yeah, at the very end of everything, everything needs to be reduced down to an S. Okay, and if that happens, then we are happy, because then our source code that we've passed was correct. So it was we didn't have any syntax errors in our source code, and we've really gotten a valid abstract syntax tree, and then we can continue working with that. Okay, so but you might already see a problem here. Just because something is the right-hand side of a production rule, it doesn't mean that it must be reduced. I mean, let's say we have a rule like arithmetic expression goes to arithmetic expression plus arithmetic expression. I mean, we have talked about ways to circumvent these problems, but let's say this is our context-free grammar, and now we get 5 plus 3 plus 2. Okay? So we might put the 5 on the stack and reduce that to an A, because it's a constant, and a constant is a valid arithmetic expression. Then we shift the plus, we shift the 3, we reduce the 3 to an A. Okay, so that now we have A plus A on the stack and plus 2 on the look ahead. Okay. Yeah, what do we do now? I mean, we could reduce this to an A, and yeah, then later we will turn this to an A and reduce these two to an A. Okay, and that would be the same as having this in parentheses. So because reducing this means that this 5 plus 3 will be evaluated first, because it's further down here. So when we recursively walk through this and we add here the results from here and here, then this will return 8 and this will return 2. So we will have 8 plus 2 is 10. Okay, but we might as well do something different. You know, we could shift the 5, reduce it to an A. Shift plus, shift 3, reduce it to an A. Shift plus, shift 2, reduce it to an A. And now we have A plus A on the stack, and we can reduce that to an A, and then we have A plus A on the stack, and we can reduce that to an A. And this would be the same as calculating 5 plus the result from down here, 3 plus 2. So this would be a right associative plus. And in case of a plus, that doesn't matter because a plus is commutative anyways. So so if we do this or this, it doesn't make a difference. But if we have a minus, then we are talking about 5 minus 3 is 2, minus 2 is 0. But if we calculate 3 minus 2 is 1, and 5 minus 1 is 4. So if we had minus instead of plus, then this would be a 0 and this would be a 4. So associativity matters in some cases. Yeah, we really have the problem that we need to decide when do we shift and when do we reduce. Okay? And this is really the brilliance of the LR parsing method, because it is a real strong algorithm for creating a pushdown automaton that can make this decision. Not always, admittedly, but it's a very strong method that works in many cases, and it works very well, so that's why I like this method so much. Okay, so let's say this is our grammar. S prime goes to S and then an EOF, end of file. Okay, this is a trick that people use in compiler construction, that they replace the S with an additional new S, and that solves some more problems, but I don't want to go into that. So this is something like an additional rule to circumvent some other problems. Okay, so the actual grammar is S goes to A, S, B, S goes to A, S, C, or S goes to D, B. Okay, now how does the LR parsing method turn this grammar into a computer program? And it uses a pushdown automaton, or it generates a pushdown automaton, and a pushdown automaton can then really easily be turned into a computer program. So yeah, that's what we're doing. We are constructing a pushdown automaton. So something that has states, a start state, transitions, and these states correspond to situations that we can encounter while we are parsing our input for this grammar. And yeah, the first situation that we can encounter is that we are really at the start of the whole process. We haven't read anything yet, we haven't put anything on the stack, and that's why we call this the epsilon state, because yeah, that's epsilon means empty, and the stack is empty at this point, at the start of the whole process. Now to analyze the situation that we are in here, we need to look at the production rules. When we haven't read anything yet, it means that yeah, we haven't read anything, so we still need to read an entire S, right? So and if we have read that entire S, then we are done, then we are happy. But at the start of it, we haven't read anything yet, and we want an S. Okay? And we signify that by putting a so-called LR information into this state. Where we put a point into the production, and this point describes where in the parsing of this production can we be when we are in this state? Okay? And yeah, as I said, if we haven't read anything yet, then we have an entire S in front of us. Now, when we haven't read an S yet, we need to read an S, but instead of an S, we could read an A as B, right? So what we need to do now is, when the point is on the left of a non-terminal, then we need to add all the productions for that non-terminal with a point at the beginning of that production. Because the point on the left of a non-terminal means, okay, in this state, we are trying to read that non-terminal. And reading that non-terminal can be done by reading any of its productions. Okay, so that's why that is done. So we add S goes to point A as B, S goes to point A as C, S goes to point D, B. Okay, so these are the things that we can be looking at initially at the start of the whole parsing process. We are looking for an S, but instead of an S, we might be looking for an A as B. Okay. And now the next step is for everything that is on the right of one of the points here, we need to create a new state and a transition using that symbol. Okay, so for A as B, we can create a transition A, and then we in here we need to take these two production rules, because yeah, if we go over this transition, it means we now have gotten an A. So these production rules will now have a point as B, a point as C. You see, because here the point was in front of an A, now we are reading an A, and now the point is behind the A. Okay. But yeah, the other two production rules die over here. So in this state, yeah, we just haven't gotten a D. So so this production rule is not something that is still relevant over here. We will have a different state over here for S goes to D point B, you know, over a D transition, but that's a different state. Okay, so let's keep talking about this state. So here now we have S goes to A point as B or A point as C. Now the point in both of these cases is again on the left of a non-terminal. So again we need to add the production rules for this non-terminal S. So point A as B, point A as C, point D, B. Okay, because after we've read an A, I mean, yeah, we can get another A, or we can get a D, right? If we get a D, then we would have something like A, D, B, C, for example, right? But okay. Good. This is the whole state for that case. And for D, yeah, if we have gotten a D, then these two cases die, this case dies. So this is the only LR information in here. And yeah, if we now get a b. I mean, here is a point on the left of a b, so now we need a successor for b. And this now looks like this. S goes to d, b point. Okay, that's an important thing here, because notice here the point is really at the end of the production rule. So this means that this information tells us if we are down here, then we can reduce using this third production rule for S. Okay, so this is called a reduce state. Okay, and yeah, many people draw this like an accepting state, but okay. So if the point is really at the end of the production rule, then that's a reduce information. This tells us, okay, if we are here, then we can reduce with this production rule. And if the point is somewhere in between, then that information tells us, no, I'm not done yet, I need more to come, so from my perspective, you need to shift something. Okay, so these are shift states. When you go into a shift state, you shift. If you go into a reduce state, you reduce. Okay, let's continue over here. Yeah, we have a point on the left of an A or a D again. So let's look at what happens with an A. Well, if we get an A, then these two cases die. This case down here dies, and we only have these two cases left, because again, after I have read an A, I cannot have moved the point over a D, because a D is not an A. Okay, so now again we get S goes to A point as B, S goes to A point as C. You know, the point was in front of an A, we walk over an A, now the point has moved behind the A. But yeah, if you look at this, we again have the point in front of an S. We add the same three production rules, point A as B, point A as C, and point DB. So what we are getting down here as a state is the same state as this one. So instead we will have a loop here. Because the set of LR informations in that state down here is the same as here. So instead we create a loop here instead and don't create another state. Okay, what happens if we get a D? If we get a D, then these four production rules die again, and we get S goes to D point B. You know, the point was in front of the D. We've read a D, now it's behind the D. Yeah, and there's no non-terminal on the right of the point, so we don't have to add anything. And then we have the same LR information as here. So instead, we replace this with an edge or a transition from here over D to here. Okay. Over here, there is a non-terminal S on the right of a point. So we also need transitions for non-terminals, which might be a bit surprising, but it makes sense later because, yeah, I mean, when you reduce something, you replace that with the non-terminal, and yeah, putting the non-terminal on the stack corresponds to walking over such an edge. Okay, so yeah, now we need an S. If we get an S, well, then A and D have died, and then we are moving only in this on this production, and then we have moved from point S. We've gotten an S. Now we are at S point EOF. Okay, and the point is not on the left of a non-terminal, so we don't need to add any more production rules. And yeah, now this this end of file, yeah, that's considered a terminal. It's more something that tells us, okay, at this point the parsing must be over. Okay, so if there's anything coming after that, then we haven't read an S, then we've read S something, and that violates our grammar, and that would be an error. So that's why you have this EOF as a special terminal that you use here, and to say, okay, the parsing process must be at the end here, otherwise we have an error. Okay, so here we have S prime goes to S EOF period, and that is an accept state, because it means we have read something that corresponds to our grammar, and then the input was also over, which we required. So this means everything was fine. We can now stop. Okay. And what happens over here? We have two rules here which have point non-terminal. So we need to create another state for an S transition, where S goes to A as point B or A as point C. Okay, again, that's these two production rules. We have the point on the left of an S, then we read an S, and then we have moved the point from before the S to behind the S. Okay, this means we are looking for an S, we've gotten an S, so we are now behind the S. And from here we don't have many options. We can either get a B or a C, and in that case we have S goes to A S B point. That's another reduce information. Or we can have S goes to A S C point, which is another reduce information. Okay, and this is the entire LR automaton for our language. And yeah, if you want to parse, yeah, let's use that. Let's go through an example. So let's say here's my stack, and my input is AA, DB, CB. Okay. Now this is my start state, so this is where I start, and yeah, that's a shift state, so I shift this A onto the stack and move over this A transition. Now this is another shift state, so I get an A, I go around this loop and shift this A also. Now I get a D, move over here and shift it. And the next thing, so this is another shift state, so I shift the B. But now, yeah, I'm in a reduced state, and it's okay to be in a reduced state because DB is the right-hand side of this production. And yeah, this now tells us to reduce this. And yeah, how do we reduce? you need to look at the length of this production. We have two symbols here, so we go back 2 steps. 1, 2. This is where we were 2 steps ago. And yeah, this going back corresponds to popping these symbols off the stack. And yeah, instead we put the non-terminal onto the stack. So we put an S here, and that corresponds to walking over this S down here. That's another shift state, so we now shift the C. And then we are down here. And that's another reduce state, which makes sense because ASC is the right-hand side of this production rule. So we remove 3 symbols. Again, we have 3 symbols here. 3 is the length of this production, so therefore we go back 3 steps. 1, 2, and we had used this loop once, so 3 steps ago we were here, and now for this ASC we now push this S, which means we go down here. Okay, now this is another shift state, so we now shift the B and go over here. That's a reduce state, which says we now pop these 3 symbols, which means 1, 2, 3. Going back here, pushing an S instead means we go here. And yeah, now we could throw in a synthetic terminal symbol for end of file, or you could deal with end of file explicitly, but I think it's relatively elegant to do it this way, because now yeah, having the end of file corresponds to reading this EOF. Now we are in this reduce state where we have S EOF point, which means we could now pop this S EOF and replace it with an S prime, which is our start symbol. So at this point we are done. The whole parsing process has succeeded. So the our input was valid, and there was no garbage behind it. So which was signified by having this end of file token here. But okay, so so yeah, this is how parsing works with this LR automata. Okay, so this was pretty cool, I think, and I think it was relatively understandable what we did here. But yeah, in reality, things sadly don't go this smoothly. I mean, this was a special grammar. This is a so-called LR1 grammar, which means that everything worked out perfectly here, because every state either has only shift informations or exactly one reduce information, you know. One reduce information, one reduce information, one reduce information, one reduce information, 0, 0, 0, 0, 0 reduce informations. And yeah, that's a nice property, but generally context-free grammars don't have that property. And that means that the states just don't behave this nicely. What will happen in reality is you might get something like a state with something like ASB point and also an CSB point, for example. And that would mean that you have 2 informations that both tell you, hey, I can reduce now, but with different production rules. You know, this didn't happen down here. There was only one, but in reality it can happen that you have multiple reduce informations in the same state. And that is then called a reduce conflict. Because if you enter this state, you don't know which production rule to use for your reduction. So that's a reduce conflict. Or you can have the situation that you have something like maybe if B then S point, and if B then S point else S, for example. And now you have one information that says, hey, the point is at the end of the production, so this means I'm done, I can reduce now. But the other information in here says, no, I'm not done. I think I would rather wait for the next token and see if that's an else. And that would mean that this information says I want to reduce, this information says I want to shift, so you have a so-called shift-reduce conflict. Okay, and yeah, that's the next big question. What do you do when that happens? As I said, this was a very primitive grammar. Here this just didn't happen, but for real-world grammars, this happens all the time. So we need a way to deal with this problem. And yeah, so far we haven't used the look-ahead at all, right? Every time we got a character, we immediately knew where to move. And we really didn't use the look-ahead, but in reality you are allowed to have some look-ahead. And normally you would have a look-ahead of 1. So for example, in this case, you would say, well, if now this thing here wants an else, if the next thing is not an else, then I don't need to care that this one wants to shift, then this is the one we are going with, right? And you could use the follow sets for this. If you remember in the video about LL grammars, we've talked about the follow set, where we would have something like if we have A as B, for example, it means that there can be a B after an S, there can be a C after an S, but there cannot be an A after an S, for example. So you would have something like follow of S would be B, C, or end of file. And you could use that to resolve these conflicts by saying, well, if let's say we have different non-terminals here, S goes to A as B and T goes to C as B. Now if follow of S is disjoint from follow of T, then we can resolve this conflict. We can say if the look-ahead is something from follow S, then we are using this rule. If the look-ahead is something from follow T, then we are using this rule. But for that to work, your follow sets need to be disjoint, and that's also something that doesn't really happen in practice that much. So if you have that property that all the follow sets are disjoint, then you have a so-called LR1 grammar, a simple LR1 grammar. But again, that's a rather exotic case of grammars. In what you do in reality is that you do some more bookkeeping. Like here, when we have this A point as B, and then we add this point A as B and point A as C, you know, and because we have this point on the left of an S, we add the productions for the S. But what you do in practice in LR1 parsing is that you keep track of what happens after the S here. So you would, if you have A point as B and A point as C, then you would add more information than that. A as B, S goes to point A as C, and S goes to point DB. Now we have the same production rules twice, but the difference that we get now is the first three are for the case where we have a B after that, and the second set of them is for the case where we have a C after that. So when we add production rules, we keep track of what happens after the non-terminal. You know, we add the production rules for S, but we keep track of the fact that this rule has a B after that, and then we say, okay, these three rules are only applicable if B is the look ahead, and these three rules are only applicable if C is the look ahead. Okay, so these are then called LR1 informations, which have an additional information about which look ahead do I require for this rule to apply. So this requires some more bookkeeping, and yet you will get bigger states, so you will need more RAM, and you will usually get many more states because two states are only equal if they are absolutely equal, including these look aheads, and it will just not happen as often that you create a new state and that new state is now the exact same state that you've already seen before. You know, it will happen more often that states are different from all the states that you've seen before, and then you get more states. Then there's one more optimization we call LR parsing, which is exactly the same thing as LR parsing, except that when two states behave the same in the sense that they have the same action tables. So with the same look aheads, you do the same things. Then you combine these states just to reduce the size of this whole thing, and that reduces the size of your final program, and that might be something nice because, as I said, in the LR1 case, these automata tend to get really big. Okay, so yeah, that's the LR parsing method. As I said, a really powerful parsing method. I mean, these look-aheads don't solve all the SR and RR conflicts. You will still encounter them in practice, but this LR1 look-ahead, it solves many of these conflicts, and yeah, this works really pretty good in practice, and yeah, that's why I absolutely advise you to use Bison, because Bison does all this stuff for you. You almost only have to tell it your grammar and it will do all the stuff for you, and it will even tell you, when you look into the Bison log file, it will very clearly tell you about these shift reduce and reduce conflicts. it lists all the states, and it even uses this notation with a point. And it gives you the action tables, which say if I'm in this state and this is my look ahead, then I shift, or if this is the look ahead, then I reduce with this rule. If I have this look ahead, I reduce with this rule, and so on. So the Bison log file is really helpful, and yeah, I mean, there are many people who tell you that you need to handwrite your parsers, and I would normally be someone who would agree with that, but not in this case, because it's so powerful. It solves so many problems so well, and so with so little effort on your side. Yeah, I mean, if you write your parser by hand, it might be a bit faster, maybe. Although Bison parsers are pretty fast, but think about it this way: you can write your own programming language in a few hours, you know. And when you handwrite your parsers, then it will take months, if not years, to write a programming language parser. So when you create a new programming language, it might become popular or not. And if it doesn't become popular, then using Bison, you haven't wasted much time. If you handwrite your parser and it doesn't become popular, then you've wasted a lot of time. So that's not a good idea. And if your language becomes popular, then, well, you haven't wasted much time doing it this way, and then you can later put in the effort to handwrite your stuff. So, but honestly, I've never been in that situation. So I've never ever been in a situation where I had to say, okay, Bison isn't enough anymore. I need to rewrite my stuff by hand. Every problem that I've ever had with compilers, I was able to use on the Bison level, and yeah, that's really a good sign in my book, because I've had a lot of problems with programming languages, and yeah, if you can really solve all of them within Bison and without doing crazy stuff around it, yeah, I think that really makes it a so useful tool. You should use it. And that's why in this video series we will be really using Bison to write our parser, and yeah, in the next video we will need to create some helper classes for representing our abstract syntax tree on the heap, because, as I said, what Bison does is not, it doesn't really create the abstract syntax tree on the heap. And if we want to have it, which I do, then we need to build it on the heap ourselves. But Bison really helps us in doing that. So yeah, we will need a few helper classes, or a few more helper classes. It's a bit boring, a bit repetitive, but we need to get through that. And yeah, as I said, next video might be a bit boring, but we need to get through that stuff, and then we will be ready to really put everything together in a Bison project and get our programming language compiler. So yeah, anyhow, that's all for today. If you liked this video, like it, share it, subscribe, and see you next time.